And let's start to create some geometry. So now I'm clicking on the normal view, and I will hide all guiders, grid, and coordinate systems. So at this moment, actually, I'm clicking to display only work coordinate system, and using the geometry tools, let's create the geometry. So let's start, and I'm clicking on the line, and my input location will be 0.0. So I'm clicking OK. Oh, once again 0.0, and then value to the right will be 68.6. Let's click apply. Let's magnify this model. Okay, and let's sketch other lines. So now I'm sketching the second line, and this will start as well from 0.00, but this time it will be vertical line, so the coordinates for that is 0.76.2. Next line will be 127.0. Next line 0 and minus 73.025. Apply, and then last horizontal line will be minus 58, for example, and 0 as the reference. Oh, excuse me. So let's start once again. So we have to start from this point, and right now, so it will be minus 58.0 as the relative value for the length. So I'm clicking OK. Now let's create a circle, and the radius for the circle will be 9.525 divided by 2. Okay, so my geometry is almost done. So now I'm going to click the intersect tool. I'm selecting all of these bottom curves. So 3 curves has been selected. I'm clicking OK, and right now I will delete unnecessary curves. Okay, let's create the face from my curves. So now I'm using the make face command, and now I'm selecting all curves, and I'm clicking OK. So at this moment, the half of the keyhole specimen has been created, and to mesh I will use manual meshing tools, because I want to create some map meshing, and due to that I will sketch again some curves, and we will imprint them on the surface. So to do that, I need to create 2 points. Okay, so coordinates for the first point are 33, and y value will be 44.2. So this will simulate the first point, and the second point will be 94 and 44.2. Okay, I've got it. So at this moment, I'm sketching some curves. Okay. Okay, and at this moment I will break curve around the circle. So just break curve. Ratio will be 5 divided by 16, for example. So I'm selecting the edge. Okay, but excuse me, I need to display the edge, standalone edge, not the edge which is associated with the face. So now I'm hiding the whole face, and right now I will break this curve. Okay, this will be necessary because I want to apply some specified number for my mesh seeding. So I'm clicking apply. So this curve has been splitted, and this part will be splitted in using this ratio of 5 divided by 11. Okay, I have that. So at this moment I'm sketching the last lines. And I'm displaying again our face. Last comment, which is related to the geometry preparation step, is the imprint. So I will imprint the curves on this face. So I'm selecting the face. Now I'm selecting tool objects. So I'm selecting this curve, this curve, this curve, and next to direction of the shortest path line, and I'm clicking OK. Let's hide all of standalone curves and points, and now we see prepared geometry. Okay, so the next step is mesh sizing assignment. So I will add some size control on the edges. So to do that, I'm selecting the curves. So for example, this one, this one, this one, this one, and these edges will be splitted to 4 divisions. And this one, this one, this one, and these two will be divided onto 5 pieces. Okay, so now I'm clicking on this 3. Let's divide them by 6. And at this moment 4 curves left. So to assign the size on these edges, I will use another method, and this time it will be linear grading by length. So I'm clicking on this option, and let's assign the start length for my future element. So it will be, let's say, 1.08, and end length will be 5.4. Number of divisions 10, and let's select the edge. So please take a look on this arrow. So we have to look on this arrow carefully, because this describes the direction for our division. So I'm clicking OK. So it was wrong, as you see. So at this moment I have to click on this select reversed object. I have to reverse this seeding. So I'm clicking on apply. Once again on that curve. Oh, I made a mistake once again. So in this case it will be just basic curve. Okay, and let's assign the size for the last two curves. It's 1.25, and length will be 6.3, for example. To avoid mistakes, we can use this preview button. So if something is wrong, I can change my selection. Right now it seems to be fine, and it looks fine as well for the other curve. So right now I'm going to the mesh, And from map face mesh, I'm selecting all of these faces, and I'm clicking on apply. So our mesh has been generated at this moment. Once again, I'm going to the geometry, and I'm going to the mesh control, and I will hide the mesh seeding. And at this stage, I'm going to apply the loads and boundary conditions. But let's click on the mesh itself once again. So now I'm right clicking on the mapped mesh and I want to display the nodes. So as you see, I used linear elements, but it will be better if we use for our model second order elements. So how to change that? To change the shape function of your elements, you're supposed to go to the parameters. You have to select 2D and change element order. This is the option related with shape function. Now I'm selecting all of these elements, and please change the order to quadratic. So I'm clicking on OK, and I'm going to hide nodes. Okay, now I'm clicking on the static and hit analysis tab, from where I will assign the constraints and loads. So now I'm clicking on the constraint button, and using advanced tab, I will select this definition, which is zeta x plane, and this provides symmetric boundary conditions to my nodes. Now I'm selecting the nodes, and I just selected 2 more, so I'm unclicking them, and I'm clicking apply. And to assign good boundary conditions, I have to fix at least one node. So I'm clicking on all of I'm checking all degrees of freedoms, and I'm clicking on OK. Okay, so the model has been constrained with the reflective boundary conditions, and at this moment I'm going to assign static load. So this time I will use the panel to the left, and I'm right clicking on the static load, and I'm choosing the force. So I will assign a force at this node, and the value for that will be 10,000 newtons. Okay, so my model is almost ready, except of material and properties. So now I'm going back to the model. I'm expanding this material branch, and using the right click, I'm going to edit the values. So for my material, I will specify the elastic modulus as 203.4 gigapascals. Poisson's ratio will be equal to 0.3, and that's all what I need to start the basic static calculation. So now I'm clicking on OK, and expanding the second branch, I'm going to define the property of 2D elements, and this time I have to define the thickness for the plate, so it will be 9.525 millimeter, and I'm clicking on OK. At this moment the model is ready. So right now I'm clicking on the analysis case, and let's start doing static calculations. So now I'm clicking on linear static, and I'm pressing solve. Before we start the calculations, I will save the model, and let's enter the name. It will be SN, let's say case number 4. save, and the process will start automatically. So the model has been calculated, and now I'm displaying the results for the shell von Mises contour. Meanwhile, I'm unchecking the geometry just for better view, and I will display also the mesh edges. So this is the contour of the shell stress of the von Mises. Okay, and right now I'm going to insert the other analysis results, and from the drop-down menu, flyout menu, excuse me, I will add some shell element stresses. I want to display the major principals and minor principals stresses. So I'm clicking on OK, and let's investigate these results. So as you see, the maximum stress is located at the notch, and the value is 338 megapascals. So right now we will start to prepare fatigue calculations using the total life method. And just to remind, probably you remember from the last lecture, but I want to remind you one more time that this method, which is called stress life, is concerned with the total life and doesn't distinguish between the initiation and propagation of the crack. So crack initiation propagation is not taken into account for this method, and this method is valid for the high cycle fatigue. And every time before we start doing these calculations, we have to think about we have to make some decisions related with the process. And for example, for the stress life, we're supposed to investigate the loading type, mean stress effects, multi-axial stress correction, and for example, fatigue modification factor, which is also known as fatigue concentration factor. So these are some points which are related with the stress life method. And in this example, so at this moment, let's say like this, let's enter the fatigue module. So I'm now clicking on Insert Fatigue Analysis Results. And the process for doing this example looks like following. So every time I need results from some static analysis set. So if we have some cases, you can choose one which is valid for your fatigue calculations. And the method which I will use, which will be total life method using the load history. This will be the first one. But of course we can use SN method using stress history, but this I think we'll show you in the next session. Today we will perform two examples. First one will be related to this, so SN using load history, and the second will be strain life using load history as well. So total life at the beginning. So under this stress option, stress type, I'm selecting the maximum absolute principle, and this is the stress parameter which will be used in my fatigue analysis. And the stress tensor from my previous results will be extracted at each node using this method. So this is maximum absolute principle, and now I'm clicking on the property. So as I mentioned before, we can choose between two methods to provide SN data. So first method is a direct input, and second method is to create the function. So right now I will select this function option, and we will define the fatigue curve. And to do that, I will copy and paste the data which has been prepared previously. So I'm using my Excel file, and now I'm selecting the SN data. So let's paste them, and you're supposed to see the SN plot at this moment. So you're supposed to know that SN curve function is divided minus is plotted in minus and fx using the stress amplitude. So in other FEA codes you can meet other options. So for example, this data is provided using the stress range. So be careful about that. In this example, I'm using the curve which is valid for the stress amplitude. So now I'm clicking on OK. And to assign this function, I have to click on Add button. So now I'm closing this property. And as the loading, I will use fully reversed load, which is related with the stress ratio -1. And due to this fact, this mean stress correction will be not necessary. So as the output request, I'm requesting the damage and fatigue life cycle. And now I'm clicking on the fatigue load. So from this dialog box, I will create and define fatigue load function. And let's create some simple fully reversed load. So it will be O, 0, 0. The second point will be related to 1 and 1. Second number 2, and the value will be -1. And the third second, again, 0. So this defines my one block of loading. And now I'm clicking on OK. And I'm selecting my fatigue load function from this field. And I'm clicking on OK. Okay, as number of the load cycles will be equal to 1. So now I'm clicking on OK. One more thing about the infinite life, and this value is related, let's say, with them in one situation. So for example, if we have some constant amplitude and some loading with some constant amplitude, and if the alternating stress which comes from this loading is lower than the lowest alternating stress from the fatigue curve, and this value will be used as the last point for our calculations. Okay, so now I'm clicking OK. And let's solve. So as the output vectors, we have two vectors, fatigue life cycle and fatigue damage. So now let's display the fatigue life cycle plot. So this is the contour map of our result, and this number refers the number of the loading cycles which are related to the loading blocks. So at this moment, this number shows us exactly the number of the cycles. So if we use the, so now I'm right-clicking on the legend to the right, and I will use the auto range command. And as you see, the plot will be slightly changed, and this will be much more convenient to investigate these results. So once again, the fatigue life shows the available life for some given fatigue analysis. And as I said before, so I will repeat this again. So if the loading is of constant amplitude, this represents the number of cycles until the part will fail due to the fatigue. And the second contour plot is the damage. And this is defined as the equation of the life multiplied by damage equals to 1. So every value greater than 1 indicates failure before the design life is reached. Okay, so it was all about the SN method, and right now I'm switching to the next model, and we will perform an example using the strain life method. So at this point, everything that you have learned about the total life method will be also applicable to the next model. And the other name of this method is the crack initiation method. So this defines that the failure criterion right now is the life to initiate a crack. So we can say that once an engineering crack appears, the failure is said to have occurred. So what we see at the screen, this is the simple model of the control arm, and right now I'm clicking on the loads and boundary conditions. So I will display the constraints and loads. So here we see the constraints. So this hole has been pinned, and the central hole is subjected to actually it will be subjected in our fatigue analysis to a fully reversed amplitude force loading on that face. But at this moment we will perform some static calculations similar to the previous example. So now I'm going to the analysis and results, and as you see, the results are loaded at this moment. So now I'm clicking on the solid stress von Mises contour map. Let's display minimum and maximum value. So at this place in this area we see some high stress, and the value is, for example, 375 megapascals. We can also go to the results and insert other output vectors, so it will be solid stresses, and let's display the principal stresses. Okay, so the result for the principal stress on the first direction, which is called A, gives the result of 400, C is 50, and B is 90. So the highest principal stress is 400 megapascals. And as you see, the yield point has been reached, and actually we have to consider the plasticity in this moment. So it's possible to investigate this plasticity using the linear static analysis, and this correction will be provided due to the Neuber's law, which is a default method implemented in Midas NFX. Okay, so the procedure looks very similar to the previous one. So now I'm clicking on the static analysis case, and I'm clicking on the insert fatigue analysis results. And from the method, I'm choosing the EN using load history. we have one analysis set. As the stress type, I'm selecting the maximum absolute principal, the same, and I'm clicking on this button to define the property. Okay, so right now the fatigue property dialog box appears, and before we start any calculation using this method, I would like to show you some information about the material and refresh the knowledge from the previous lecture. So let me show you the Excel file. Okay, so on this page we see the cyclic stress curve and monotonic curve, and these two graphs has been plotted on one graph, and this plot shows how our material behave under cyclic and monotonic loading conditions. So these parameters, which are referred to the strength coefficient, strain hardening exponent, and cyclic strength and cyclic hardening exponent, need to be defined in order to characterize plots according to these equations. These equations relates stress amplitude to strain amplitude. So if we take a look on this, for example, this equation, which is called Ramberg-Osgood equation, and you remember this equation from the lecture, the first part to the part related to the left is related to the Hooke's load, and this part defines the plastic strain. And this is the equation for the monotonic curve. And the only differences, if we compare these two equations, are the primes, which are providing the information, which are providing to us the information about the cyclic condition as the opposed to the monotonic condition. So these curves has been created from these parameters, and you remember this table from the lectures, and I took these parameters from this table. So I created the monotonic curve and cyclic curve. So if we take a look on this cyclic curve, we see that yield point of our material is above the monotonic, which implying that is stronger under cyclic loading, and this is known. This phenomena is known as the cyclic hardening, or we can say strain hardening, and I was mentioned about it during the lectures. So when a material softens, other cyclic material properties, this can be very bad for very bad for your structure, and very bad from a durability point of view. Okay, so we have this curve, and now let's take a look on the stress strain life. And this is the curve which will be implemented into MIDAS and FX. So to the left we see the coefficients and parameters which are related to this Koffing-Manson equation, and this curve can be fully characterized by knowing of these material parameters. So like the stress strain curves, it's also split, or we can say broken, into an elastic component and plastic component, which can be also plotted separately. and I have plotted these components using this elastic and plastic asymptotes, so you can see this. Okay, so if we what is the strain life curve? Strain life curve is the summation of these two, and the elastic, this is elastic and this is plastic line, so these lines cross each other at the point which is called the transition point. So to the left of this transition point we have low cycle fatigue, and to the right we have high cycle fatigue, and the equation looks very similar to the Baskin's equation, and this proves that strain life method can be used as well for the high cycle fatigue. Okay, as I said before, in order to calculate plastic strains, we will use the Neuber's load, and I'm talking about this because now we have a curve, but we can use let's say nonlinear response of our model using nonlinear static analysis, and we can create our curve as well. But today we are using this data. So now I'm switching back to the MyDOS-NFX, and let's enter these values. So 1043 as the fatigue strain exponent. Let's enter 107, 309 for the ductility coefficient, and minus 481 for the fatigue ductility exponent. So now I'm clicking add, and the material has been assigned. So I'm clicking on the close button. Under mini-stress correction, I'm unchecking the Morrow and Smith-Watson-Topper correction methods because I will use fully reverse loading as well. So output request is damage, fatigue life cycle, and let's define the loading. So let's define the same sinusoidal signal, and now I'm clicking on the, I will use again my Excel, and now I'm copying this data to define my fatigue loading. Copy. Now I'm pasting this, and let's add the name. So fully reversed loading will be the name. So I'm clicking on OK. Let's select this loading, so fully reverse loading. Let's click on OK, and let's click OK to accept the fatigue analysis settings. So now I'm pressing the solve command, and let's display the results. And here we see the fatigue life cycle result for the specified material and for the other model, and we can also display the maximum damage result. So it was all for today for the fatigue analysis and for the simple examples. I hope